Hello, this is Schwab again. Welcome to the next presentation. This time I'd like to show you a very simple and easy calculation, but calculation which I really like. I've prepared here some of the geometries. Let me start with this simple flat die example. This is a flow channel in a flat die which is used to make a flat film. So if you want to make a flat film, you typically bring the polymer in a round pipe, and you have a round channel or a shaped channel which is distributing the mass to the sides. At the same time, you need to have a restrictor which creates some resistance, and that resistance is longer here, shorter there. That's why the polymer flows to the sides and should gradually leave. I would like to see whether we have a good distribution at the exit, what are the stresses, and so on. Now, you can do this in a 3D finite element calculation, but if you want to have, let's say, 4 or 5 elements at least across the gap, and you can see the gap is very narrow, you will need probably hundreds of thousands of elements, sometimes even millions, and the quality, the convergence is very poor, and the quality of the solution is quite doubtful because the elements tend to be squeezed, stretched, and the 3D film solution is not really a winner here with this very narrow gaps. Well, in this case, however, all the resistance is more or less created by the shear flow and this resistor. And so probably we can do some simplification, and that's what the Shell model does. Basically, if I'm showing you this 3D geometry, in fact, what we have used for the definition is much more simple. It is simply a series of triangular elements, which are shell elements, with a certain thickness. So let me show you the mesh used here. Okay, this is the mesh being used. You see lots of triangles, which are flat really, but these triangles have some thickness in the nodes. So the thickness information is contained in the nodes. We also can see that we have here also a kind of relaxation chamber. So every element has its own thickness. We have restrictor, relaxation chamber, lips. At the same time, and we can have line elements here and also there, which can represent either tube or annually or planar flow, and we can make a combination of those two and create very efficient mesh, which is basically a network of flow resistances. So this is creating the same situation, the same results as the 3D film solution. Um, what is the advantage of this calculation? Why would I simplify so much? Well, that's because with this kind of calculation, my solution is much faster than it would be in 3D FEM. This, what you see here, is a real-time solution. I didn't speed it up. It's just started right now, and I'm calculating. And you can see the pressures and other variables are being updated during the solution, while they're updated after every 50 iterations. And we also can have the calculation is done maybe in 1 or 2 minutes maximum time. We don't need too many iterations, probably something like 90, 120 iterations would be very sufficient for a good quality solution. The solution calculates not only the pressures, but it calculates also the velocities, temperatures, and other results. Okay, the solution is done, and we see the pressure contours. We see how the polymer is flowing here. At the same time, we can look at the, let's say, average velocity, and we see the polymer having much higher speed over there, and much higher also at the lips. We see some slowing down the relaxation chamber. Now the velocity field is a little jagged. That's because the mesh should be still refined to have a smoother solution. But if you would solve it in 3D FEM, you would see very similar pattern and you would see very similar results. Of course, we need to know what is the distribution at the exit. Well, first, let me show you a small thing. I didn't use the whole die. I was using a half because it is symmetric. This was only a view, mirroring view. Okay, and we can now go and say, and we can just pick this exit, and we see that right at the exit, my velocity is high at the edge, and small in the center of the die. So now I need to adjust it. Of course, adjusting would be relatively complicated on this mesh, which is having lots of triangles, right? But there is a definition mesh behind this thing. Again, it is symmetric, so I can look only on the symmetry. And this definition mesh consists from only several quads and only one line. And also there is a line over here for the manifold. So it's very simple to adjust this grid. I can just move this point, let's say forward like this. And when I do that, it's very simple just to say solve, and he automatically generates this mesh and solves it. Let's see. Okay, now the mesh has been generated, you see, and now it's being solved. So it is very straightforward, very fast, easy to do. And if we wait for 50 iterations, we will end up with a solve. Yeah, we already have velocities, and we can look also on the pressures and see how the polymer flows. Okay, so this calculation is really very fast, and it's prepared for easy adjustments, change of dimensions. What more, of course, I can very easily do undo. I simply do undo, and my mesh is just back at where it was before. Um, Also, I can simply adjust those thicknesses and just say resolve, and I will be having completely new solution again. Okay, so this is again my solution, and if I wait like for 90 iterations, it will be converged, and I can post-process. The post-processing is able to show me different kind of variables. I see also the velocities, but also we can see, look at the temperatures. At the moment, the temperatures are not correct, but let's wait for an update. All right, these are the temperatures, and we see a cold polymer coming in. We see the due to dissipation, the polymer heats up, and it heats up more where we have more mass, of course. So we have it red. If you would look at the 3D film results, I guarantee that you get more or less the same results. This is really very close to a final solution. And as I said, we can look at the velocities, temperatures at the boundaries, and we can do different post-processing. What it also is possible is we can just let's say pick a streamline when holding control. I can choose a seed, and then I can trace a particle going through that geometry. So this shows me velocity on that particle. So I can do similar things like I do for normal 3D meshes. Okay, but I gain the simplicity, I gain easy mesh generation, I gain easy adjusting, change of parameters. So when somebody needs to design initial design, this calculation is really very fast. Okay, we have of course other types of geometries. I'll show you this one. This is very interesting. What if we want to do a pipe like this? This is a flow in the spider die. When we bring in the mass in the tube, we have an annuli here, a torpedo inside, which is being held by the supports. The shell model is able to do also the support, but at the moment I try to use very simple thing. This is the definition file. Oh, now you're probably surprised because we see only 5 lines. Yeah, but this line is treated as a pipe. It has a parameter, it has a type that it's a pipe. These lines here are named annuli sections. So if I want to see them in the graphic representation, the 3D representation, I see them like this. So it's very simple to, let's say hide these sections, and we see the annuli there. We see how these pipes are being represented. Okay. Now, when you just click solve, the mesh is generated right now, and now this calculation starts. If I show you the real generation mesh, this is the shell elements being used. So you see they are much denser than the definition mesh, but they again are lines with certain parameters, and we only visualize those parameters like this, like a regular real a die. Now, in fact, the solver also knows that this is, annuli here of certain diameter, inner and outer. And now we see that in front of our eyes, the calculation is going on. And after a few more iterations, we are ready. Uh, Again, we can look at the pressure, we can look at velocities, we can look temperature, but we can also look at the stress here. So I can look at the stress. Okay, it's not coming yet. Oh yeah, now this is the stress. We see very large stress at the exit lips, and we can do shear rate and other properties too. Also, if I use this kind of representation, I can, let me stop the solution. I think that's sufficient. I can very easily say, show me the value boundary grid. So I pick just this whole thing, and I'll be having pressure along that pipe die. I'll be having velocity, right? So we see how in this annular section, and if you want to see it again, you can just do, and then of course you'll be having the 1D line inside, so it's sometimes difficult to see through, but yeah, we're moving through that section, and we're visualizing what is the velocity basically on that domain. We can of course do much more complicated things. This is interesting here. What if I need to solve a distributor? Because the shell elements allow me to combine tubes, flat elements, annular sections, planar sections in many different ways. So if I, let's say, want to get the same amount of flow coming out, and if I solve it, of course, that this is the pressure. Let me show you the velocity. Of course, this one gets much more flow than that one because it's much closer to the entrance. The polymer comes from here and it's just closed over there. So that one doesn't get enough. Well, we can then very easily play with those gaps or diameters because those are only parameters. What I have done, in fact, was only a series of lines. These are the lines, and I can just change the diameter of as a parameter of this line, and then I can simply change the shape. I've done it. I've done it here. This is the shape changed. Okay, and that's the shape solved. So if we're looking at the velocities, nothing's easier. We now have that the velocities. Again, we have high velocity here, but the velocity is not doesn't matter. What matters is the mass flow rate. So we need to multiply by area, and then we get whether the mass flow rate here and there is the same. Well, I know it's a little bit more calculation. That's why I've prepared here a very small trick that I have added at the top of each of those pipes a small extra segment which doesn't consume any pressure, so it won't have influence, but it has the same diameters, the same area. So now we just can look at the velocities, and if the velocities here are the same, we will be having the same flow rate in those sections. We also have another type of geometry. This is interesting here. That's a flat spiral die. Okay, we see polymer coming through, and then it's split into two streams. But we see here only one stream, and again that stream is split into two. So this should have, in fact, 1/4 of the polymer. This is having full flow rate, half flow rate. This is 1/4 of the flow rate because that represents only 1/4 of the die. Well, the shell model allows to specify that in these elements there is only a fraction of the initial flow rate, half of it. Here only 1/4. Also, it allows to use a periodicity boundary condition because we have this geometry periodic. What comes out here should enter here. If I show you the solution, this is the pressure field which indicates that we can very efficiently solve that one. I guarantee the solution runs in like 1 or 2 minutes, and it's very similar to 3D film results. We also have reliable velocities and pressures. On this mesh, this particular mesh has been relatively rough. You see the elements are quite big. I should refine this. That's why also my velocity is a little jacked. But I can immediately say, show me the values at the exit. And if I say, let's say, I want to go from here to there, I'll be having the velocity at the exit of my flat spiral die. Well, that's really interesting. I can look also on the temperatures and shear stresses and any other variables, and I can very fast design a die like this. So to me, this is a very good thing. This was the definition of the grid. Again, if you look how it looks like, This is the simple definition. We see a line, another line. You see they're even not connected, so that shows another simple trick, which I will demonstrate probably on the next domain. This is the one. That's another example. What if we want to do a flow in a die like this? This is a flow channel in the die. So we like to make a pipe for getting the rainwater out from our house. And that's an oval shape. It's not a round, but oval. And we are getting problems that the distribution of the oval is not the same. And we're trying to design the flow channel the way we want. Well, it's very simple to make this. First of all, let me say that it is symmetric, so we could be solving only one quadrant. At the same time, I can say, okay, well, the definition doesn't need to be that complicated. We just need few elements here for that one quarter. I need to have these. But here I can have a line, because if I specify that the line here is a pipe, this one is annually, I will be having something like this. And then when I generate it, it will be really getting me this kind of solution. Interesting thing is that here we have a special types of boundaries, which let's say join this node to these ones, saying that there is the same, that it's joined, that there is some same pressure value. So, and also the temperature from here, or the heat from there, it's feeding these sections. So if you look at the results and you analyze the pressure, you see it looks like really it is connected. Of course, here for these kind of elements, I have to specify that they have only a fraction of the total flow rate. They have only 1/4 of the total flow rate, but that's the Shell model allows that, and we use it very often. We also can look on variables like velocity, for example. So we are seeing that the velocity at the exit is not even, and again we can look at temperature too. Okay, but it's only 1 degree of viscous heating, so it's not that strong. If we look at the temperature, we can say show me the flow at the boundary. And if I now show you the full shape, we will see that right here I have much more mass than over there. Well, that's clear because it is much longer distance from this point to here than from this point to there, because of the different diameter, right? So this is very useful again to use that shell model. Well, the main power of the shell model is of course in geometries like this, where we have really a complicated profile die. You see, this is a profile die solved by 3D FEM. This is a 3D FEM model. It has two geometries. One, which is fed from the bottom, so there are two polymers, and then there is the other one, which is fed from the side, and they're only connected over there. Well, this solution took me a couple of hours, really. It was solving for about 6 hours. And I'm not talking about preparing the mesh. The mesh generation was like nightmare. Now, if you look at the solution, the Helio solution, you probably will have difficulty to even see any difference. This is showing me the same effect, the same pressure values, in fact. I see the same, let's say, kind of contours. Look, for here, we see a little bit darker color there. We see a lot of pressure being consumed in the parallel region. The same is here. We see a little dark color and a lot of pressure consumed. If you compare those values of pressure, you will see hardly any difference, if then it's just few percent. So the shell model is really giving us the same resistances as the 3D model. It's really giving the same results, but it's giving it in terms of minutes rather than hours of calculation. Of course, here we face some troubles with creating the mid-plane mesh. So for sure, the use of shell model will be limited to cases where we can easily do that. However, we have created here lots of new operations which simplify this approach and which will help you to make it much more efficient. Okay. That's the introduction to the shell model. I'll be presenting each of these examples separately, so feel free to look at my next presentation. Thank you very much. Bye-bye.